Hello. So today I thought that I would go ahead and share with you a little derivation for how to find the capacitance of a capacitor that is cylindrical. So cylindrical capacitor. So taking a look at this, you'll recognize this from your packet. One small note, and that is that right here uh, on your original, there's a typo. It tells you that the length of the capacitor is lambda. That is not correct. We intend the length of the capacitor to be L. Alrighty. So, taking a look at this, we have basically two pieces of metal. There's an inner cylinder and then an outer hollow cylindrical shell. Together, these are going to be the two conductors that make up the two sides of the capacitor. What we want to do is find the capacitance. Got to charge positive Q on the inner shell, negative Q on the outer shell, and that's basically it. Inner radius A, outer radius B. So let's find this capacitance. So the way we're going to do that is we're going to use the capacitance formula that says, hey, capacitance is going to be my charge per volt. Okay, and again, in the capacitance formula, that delta V, that is the change in potential from one side of the capacitor to the other. So in this case, that'll be the delta V from, say, the inner piece of metal, that inner cylinder, to that outer cylinder, the delta V from one to the other. So you say, well, gosh, that means that if I'm going to go ahead and do this calculation, I'd have to figure out what the delta V is. You say, well, to find delta V, we want to find the change in potential from one location to another. So we're going to use this path integral form of voltage equation, negative integral E dot dr. Okay. And when we do this, we're going to go ahead and apply it here along a path from one side of the capacitor, dot, 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 to the other side of the capacitor. So our path is going to be going from R equals little a to R equals little b. So I'm going to put those bounds on there. Oops. From A to B. Okay. And you say, well, great. Of course, I'd love to go ahead and do that calculation. But to do that calculation, I have to first know the electric field strength. So I'm going to get the E value from doing a Gauss's law calculation. So I'm going to go ahead and say surface integral, E dot dA, integral over closed surface. And that's going to equal my Q inside over epsilon naught. So I recognize I'm going to have to do kind of this chain of calculations to get to my final answer. So I'm going to start by finding the electric field strength using Gauss's law. This is, of course, a calculation that we did in previous unit, but I'm just going to really quickly crank it out here. It's pretty quick to do. So you say, okay, starting off, integral E dot dA is my Q in over epsilon naught. And you say, to do this, I have to make a Gaussian surface, choose a boundary. The suggested Gaussian surface is shown there. We're going to go ahead and we're going to do a Gaussian surface that goes around this, right? And then goes on down here and closes, right, on itself around that inner cylinder, right? Okay, that inner cylinder is going to continue on down here, right? Right. Okay. And so I can see my Gaussian surface here. It's going to have a length L, right? And it's going to have a radius here that is just a little generic little r. Okay. So I'm setting it inside where r is between A and B, inside there in that area between the two sides of the capacitor. So when I do that, you recognize that as I go from the inner surface to the outer surface, yeah, the E field strength is going to be changing, but by symmetry, looking here on that right diagram, I see that anywhere on this Gaussian surface that I'm drawing in here, right, anywhere on there, that E field is going to be the same strength, right, by symmetry. Those E field lines will be spaced the same separation distance. It'll be the same strength everywhere there. So that means that E is a constant. Actually, before I say that, I should say a few words about the dot. Right? You say because it's a dot product, E dot dA. You remember that little area vector guy for a Gaussian surface? You say, hey, that area vector, it always points which way? You say straight out of the surface, right? Perpendicular pointing outward. So like here, my little dA, little bit of area vector would be going parallel to that E field, right? And that's going to be happening anywhere along here. My little area vectors will be going parallel to the E fields going outward. And so that's going to mean I'm going to have a cosine of 0 degrees on that surface. If you think about it, my little Gaussian surface here, it's got kind of this top surface here, right? And a bottom surface down here, right? Sorry. But you say there's not going to be any flux going out the ends, the top and bottom of this blue Gaussian cylindrical boundary surface that I did. There's no flux out the top of the bottom, so I don't have to worry about those. I'm just worried about flux out the sides, and it's going to be going nice and perpendicular to the area parallel area vector, perpendicular to the surface. So that means that when I do this Gauss's law calculation here, of course, you say that right. You say this is going to be a cosine of 0 degrees when I do that calculation, which is just going to be positive 1. The E is constant around that surface, so the E pops out. So what's going to be left is E times that integral over a closed surface dA, okay, is equal to Q inside over epsilon naught. And you say, what is the Q inside anyway? And you say, well, the Q inside is just the Q on that inner conductor, the inner cylinder, which is just positive Q, big Q, over epsilon naught. You say, okay, so I just got to figure out what this area is. You say, what? Now, we already figured out that I don't have to worry about any flux through this top surface or through the bottom surface. The only flux is going out the sides of this blue Gaussian surface. So I need to figure out what the area is of that side. Well, to do that, I would just go ahead and I would take this guy. I would slice it down the side and unroll it. And wouldn't it make kind of like this long rectangular sheet? And you say, well, this dimension would be L, and this dimension is just going to be the perimeter circumference of that circle, right? The circumference of the circle, which is just going to be 2 pi r. And so then I can see that that area is going to be 2 pi rl, is the area of that Gaussian surface that the flux is shooting out through. So coming on to the next line, you say I'm going to get E times 2 pi rl is the Q inside big Q over epsilon naught. Rearranging, I'm finally going to get that E is Q over 2 pi rl epsilon naught. Okay. Now, a lot of people like to talk about, hey, what if I took this cylinder and I made it like really long, right? Really long. What you'd have basically is a coaxial cable. It'd be like you'd have some insulation in between here, and have a coaxial cable. And so we might be interested in knowing like how much charge I can store up per meter of length or something. So I might be interested in knowing my charge per length, right? If you will charge per length, I recognize that. We talk about the charge per length. We usually give that the symbol lambda. So if I wanted to write this in terms of lambda, then I might write it as 1 over 2 pi epsilon naught, right? There'd be times a lambda, because that's the Q over L, right? This part here, that'd be lambda. And then I have 1 over R, right? And so we could write it like that. Some people might say, hey, look, that 1 over 2 pi epsilon naught, that looks an awful lot like the Coulomb's law K. Remember, the Coulomb's law K is 1 over 4 pi epsilon naught, right? So if I wanted to, you could also say, hey, this is equal. I don't know why I did a little squiggly. It's actually directly equal. I could also call this, that would be, so then 2 times Coulomb's law K would be 1 over 2 pi epsilon naught. So I could write this as, 2 lambda K, right, times 1 over R. Might be a nice tidy way of writing it. Now, there are good reasons to not use the Coulomb's law K. I usually use Coulomb's law K when I'm dealing with problems with spherical symmetry, because it's just really easy, or with point charges, knowing that electric field strength is KQ over R squared, or that the electric potential from a point charge is KQ over R. It's really quick and easy to remember and work with. But once I have other geometries, I generally try to avoid using little Coulomb's law K, because I don't want it to get confused with kappa, okay, which is a different thing that's going to be involved in capacitance problems. So using lowercase k in a capacitor problem is probably not a good idea, because people might confuse it and think it's your kappa, okay, your dielectric constant. Okay, that we use the symbol kappa, and kappa looks too close to lowercase k or capital K. So I try not to use lowercase k in problems like this. So I'm gonna go ahead and do this Well, you know what? I'm just going to go ahead and use the full, with all the variables version here. I guess the nicest way for us to write it for right now would be probably to write it as Q over 2 pi epsilon naught L times 1 over R, so that that variable is like popped out here, right, by itself. That little, this is proportional to 1 over R, my E field strength. Okay, leaving it like that. Hey, now we have the E field strength. Now I have that, I can plug it in here and do my delta V to find the potential difference from one side of the capacitor to the other side of the capacitor, from one plate to the other plate. And so when I use this form, so now we are moving over, we are done with the Gauss's law calculation. We got out of it what we needed to get out of it here. So now we have that E field strength plug into this path integral voltage equation. So we do delta V is negative integral E dot dr, going from the inner plate to the outer plate, A to B. I'm going to switch colors here. So I'm doing delta V negative integral E dot dr, going from the inner plate A to the outer plate B. From that rate, R equals A to R equals B. When I do this, I chose to go from the inner to the outer. You don't have to go that way. You can go from the outer to the inner. It doesn't matter, because for what we're doing here, going one way, if I go from the inner to the outer, you notice I'm going along the E field arrow. And when I go along the E field, that dot product, right, is going to end up, for this case, being, if I go from A to B, it'll be the cosine of 0 degrees, which will just be +1. And this negative in the formula, though, will make that a negative change in potential, which makes sense. I'm going from a positive, near a positive charge to near a negative charge. I should be going down potential. My V value should be going down. And this negative is definitely needed in the form to make that happen. If you look at Viren's videos, he will oftentimes reverse the bounds. In other words, he'll go backwards. He'll go from B to A, right? And then that will effectively like flip the sign for him. And so then he just like takes the absolute value and it gets rid of the negative. And it's like, which I find confusing. I wish he didn't do that. I wish he stuck with the formula as it is based on. So just be careful about that. I'm going down potential here. I think the reason he does that is he's choosing, like planning ahead and choosing so that he gets a positive out for delta V. Because when we use the capacitance formula, we always just take the absolute value anyway. But moving onward, for our purposes, someone wants to know the delta V from here to here, you better be able to say whether it's going up potential or down potential. And so being very careful about your dot product and the negative that is built into this formula is important. Okay, so getting back to this, we are choosing to follow a path. Anytime we take a delta V calculation, we're going from here to there. And like I said, the sign will be different if we go from there to there. So we want to go from the inner to the outer, from A to B. So I'm going right along the E field line. So my path, my little DRs from here to here to here to here to here to here, going along from the inner to the outer, are going right along that E field vector. So it is going to be cosine of 0, +1 coming down here. So when I do this, negative integral from A to B, right? And again, this is just going to give me a cosine of 0 degrees because I'm going right along that +1. And so I'm just going to have EDR. And you say, well, that E is not going to pop out because E is not a constant as we go from the inner to the outer. You can see the field lines are getting spread more further apart as I go outward from the inner plate to the outer plate. And so you say, oh, gosh, I'm going to have a decreasing E field strength. I better put in the function. Oh, look, E is a function of R, so it makes sense. It's changing. If I substitute that in there, you say, hey, I'm going to get negative integral from A to B of what I get. I got Q over 2 pi epsilon naught L 1 over R, right? And then I have my dr. Okay, and that's my calculation. You say, hey, look, all this chunk at the start here, these are all constants as I go from the inner plate to the outer plate. So all those constants are just going to kick outside of the integral. So I'm going to have that my delta V is going to be negative Q over 2 pi epsilon naught L, right? I just have the integral of 1 over R dr from A to B. You see the integral of 1 over R, that is going to be a natural log of R evaluated from A to B. If I go ahead and do that, that'll be the natural log of final minus initial. natural log B of minus natural log A. And a special property of logs, you might remember, is that when I have a subtraction of things with the same base, I can just turn that into a division, B over A. So the natural log B over A is what that integral part there comes out to be. Out in front, I've got this negative Q over 2 pi epsilon naught L. Okay, and that is my delta V going from A to B. And I'm getting, you'll notice, a negative answer out, and that's okay because I'm going from the positive plate to the negative plate of my capacitor. I'm going from high V to low V. It should be a negative delta V. Now they'd like us to go ahead and find the capacitance. Finally, we can go to find the capacitance. I'm just going to take Q divided by delta V. And so that final last piece of this calculation looks like this. You say capacitance is my Q per delta V. And so you say, well, gosh, that's just going to be Q over, and now my delta V was this whole mess in green here, right? So that's just going to go in there. And so it's going to be Q over 2 pi epsilon naught L, right? And then times natural log of B over A. You say, now when I do this, right away you notice something that disappeared going from there to there, and that is that I went ahead and I got rid of that negative sign. Why did I get rid of the negative sign? Because capacitance always is reported as a positive value, right? We always do that. And so I want to make sure that what I'm putting in the denominator here, and this whole thing, right? You say the Q's are going to cancel. And so I'm going to end up with a negative or a positive value. I want to make sure. You say, well, gosh, 2 pi epsilon naught L, the length of these are all going to be positive values. What about this natural log B over A? Well, I remember that like natural log B over A, you're like, if I go ahead and I do that, right? You're saying, as long as, since I know this is really like a log base E to what power gives me B over A? And you say, well, I know that E, the power to the E, right? You say, I need B to be bigger than A, as so that I get a positive power of E, right? You know what I'm saying? And so as long as B is greater than A, I'm not gonna sweat it. If I had A over B, then I might have to worry about needing a negative exponent, and I want my capacitance to be a positive value, and so I'd have to worry about that sign there. But basically, I'm just dropping the negative sign that was there. I'm just going to go ahead and get rid of that negative sign that was in the delta V, because it doesn't matter for my purposes for capacitance. I just want to know how much charge I can get stored up, how big the Q is here for every volt I put across this thing. I don't care about which one's positive or negative. I'm just trying to find my charge per volt. So capacitance is always recorded as a positive value. So just make sure that whatever I did here, I'm going to get a positive out in my final answer. Okay, and so that means I got to drop off a sign like I did here. I will do so. Rearranging this mess, I'm dividing by a fraction. It's going to multiply by the reciprocal. So it's going to be 2 pi epsilon naught L over the natural log of B over A. Okay, and that is my capacitance for my cylindrical capacitor. You'll notice that the capacitance, right? Take a look at the values of what it depends on. 2 pi constants. B and A and L, those are just measures of the size of the capacitor. In other words, none of this has anything to do with how big of a battery you've hooked up to it. The capacitance is a set value that just depends on the geometry of the capacitor. And there's one more thing, and it's kind of hidden here. You don't, until someone points it out to you. This epsilon naught value is a universal constant, right? But it's specifically, when you see that little naught on it, that's the vacuum permittivity, it's called, or the permittivity of free space. And you say that's a value that actually only holds if you have empty space between the two metal plates. You have a vacuum. If I put a different material in between the two metal plates, some kind of an insulating material, we call that material a dielectric. And what that will do to this calculation, instead of epsilon naught, instead my new value that I put in there is kappa times epsilon naught. That goes in my new epsilon. Okay, the epsilon with that dielectric in it. Okay, and that's what I would use in the calculation. So like if you want, there's like a little kappa that would be hiding here next to that epsilon naught. If I have a vacuum, for vacuum, dielectric constant kappa for a vacuum is by definition equal to 1. And so that's why I'm not showing it here. And the kappa for air is approximately equal to 1. It's like 1.00059 or something like that. So the point is, we'll talk more about dielectrics at the end of this unit, but this is what that formula looks like. And if I had to have a dielectric, I just slip a kappa in there to fix it. And that is it. And notice it would just multiply this by kappa. And so like my new capacitance for the capacitor with the dielectric would just be equal to that kappa times the old capacitance in blue here. You know what I mean? If I put the kappa there and the kappa there, right? You know what I'm saying? And that's how that would work. Okay, I am going to, this is like my old capacitance without the dielectric. Okay, that's it. We should probably, now the other geometry that is we want to be able to solve for, besides parallel plate, is spherical. And I believe Viren does a fairly nice job of walking through this one. He probably talks about it a little bit differently than I would in a few parts, but I'm going to just let that go for now. So that's it for this video.